everybody, welcome back to another lecture video. Today we're doing chapter 4. Chapter 4 is all about atoms and elements. So let's just jump right in. So we've already been talking about atoms. We know that atoms are the smallest component of an element, and we know that elements are different by the number of protons or neutrons. Well, protons determine the element, neutrons determine the isotope, but we know that the insides of the atom are what ultimately decides what kind of atom it is. And we also know how to classify either pure substances or compounds. But today we're going to start focusing a little bit more on how we quantify these types of things. Now, atoms are the foundations of our senses, right? If we can see, it's because light interacts with our molecules in our eye and with retinol. If we can taste, it's because the chemical substance that atoms in the structure of sugar, let's say, or caffeine interact with the receptors that are made up of atoms and molecules in our taste buds, right? So typical seaside rocks are composed of silicates. I'm trying to show you a seaside rock here, though I don't think I have a picture of it, but kind of focusing in here. And seaside air, for example, also contains nitrogen and oxygen molecules. Silicates, I didn't go into that any further. Silicon atoms and oxygen atoms together. Seaside air can contain substances called amines. Amines are nitrogen-containing compounds. This is an amine right here, and this actually looks like it's trimethylamine. Triethylamine, on the other hand, is what usually gives the fishy smell to fish and is emitted when they're decaying. It's also triethylamine that contributes to the fishy smell in general of the seaside. This is often why people add lemon juice to their fish, because triethylamine or trimethylamine is a base and lemon juice is an acid, and it neutralizes it, forming a salt. And a salt, we call it a salt because it has a charge. Usually there's a counter ion as well, and then it doesn't have that smell anymore. So really the changes in structure give rise to changes in the properties. Now, as I mentioned, this chapter is all about quantification. So how do we know how many atoms there are, let's say, in a pebble? Well, atoms are incredibly small. A single pebble from the shoreline in this example might contain more atoms than we could ever possibly count. The number of atoms in a single pebble actually far exceeds the number of pebbles on the bottom of the San Francisco Bay. So that the actual number of atoms within a pebble is bigger than the number of pebbles. To get an idea of how small atoms are, imagine if within one pebble, if every atom inside that one pebble was actually the size of the pebble itself. So picturing, a very, very small, pebble, one of these little rocks. Inside that rock, you can imagine that it's actually made up of lots of little atoms. If every one of those atoms was to itself be as big as the pebble would actually be larger than Mount Everest. And that's what I'm showing you here. So just trying to imagine the compactness of that many things, right? As many pebbles as it takes to make Mount Everest, that's how many atoms would be inside one of those pebbles. Now, atoms compose matter. The properties of atoms determine the properties of matter. An atom is the smallest identifiable unit of an element. And an element, of course, is a substance that can't be broken down into any simpler substances. We know that there are 91 elements that occur naturally, so 91 different kinds of atoms. Now, scientists have been able to make about 20 elements in the lab. The exact number of naturally occurring elements is actually controversial because some elements that were previously considered to be only synthetic might actually occur in nature in small quantities, so we don't really have a good answer for that. The atomic theory was developed by Democritus, and he came up with it because it was what cannot be divided. Atoms actually means indivisible in what is the language? I don't know what language he spoke, but it comes from the word atomos, which means individual. Now, Democritus is the guy that I'm showing you, and he's one of these guys in this picture here, and his mentor, Leucippus, maybe that's how you say his name, Leucippus. These guys were thinking about, remember in the old days it was all about thought, what would happen if you take matter and divide it in half, and then take that and divide it in half, and that piece in half again, and what would happen? And eventually they got to the smallest bit that they said would have to be indestructible. It would have to be an indestructible particle, or else you could go on forever. And that indestructible bit was the atom. Now, Democritus is the first person on record to have postulated this, but some other people may have actually thought of this before. Now, the atomic theory of Dalton is a little later, 1808, compared to, I didn't give you the date on this, Democritus, around 400 to 300 BCE, so before the Common Era, before the counting upwards. This was going backwards. So in 1808, about 2,000 years later, roughly, John Dalton, a different guy, he actually formalized a theory of atoms that gained pretty broad acceptance, and there's 3 parts to it. The first part is that each atom is composed of tiny, indestructible particles called atoms. So elements come from atoms. Or I guess I should say, each element comes from tiny, indestructible particles called atoms. The second sort of part of his atomic theory is that all atoms of a given element have the same mass and other properties that distinguish them from other elements as atoms. So atoms of a type of element are all the same. The third part of this is that atoms combine in simple whole number ratios. Combine in simple. And this means we don't get half of an atom ever pairing up with 4/10 of another atom. They're always 1 to 2, or 3 to 1, or 5 to 5, which I guess would be 1 to 1. And actually, there's a lot of modern evidence for that particular idea that atoms are a thing. We've been able to. I've shown you a few pictures of atoms. In fact, IBM was able to make a logo, an image of their logo, using xenon atoms, and they used a scanning tunneling microscope to move them around. They took it a step further. They actually animated a little stick figure dribbling a basketball, and they did it with atoms. And so these cone shapes of the atoms are actually, as I mentioned earlier, due to the instrumentation, but we think that atoms are in general spherical. Now, how do we get to that? Some of that has to do with physics, charges and fields and that kind of stuff. We like to look at symmetrical things, but in the early days of electricity, when we were able to start playing around with electricity, there was an English physicist named J.J. Thomson, and he discovered that there was a smaller, more fundamental particle within the atom called an electron, and that this electron, it was negatively charged. They knew that they were much smaller than the lighter atom, smaller and lighter than the bigger atom. Sorry, the electrons were uniformly present in different kinds of substances. It didn't matter what kind of material, there was always electrons present. And he proposed that the atoms must contain positive charge that helped to balance the negative charge of the electrons. Okay, and so there was something called the plum pudding model. Probably because it looks a little bit like plum pudding. I guess that's not something I'm too familiar with. To me, it looks like a chocolate chip cookie of some sort. So I'm going to call it the chocolate chip cookie model. But the model suggests that the negatively charged electrons, shown here in yellow, are just held in the sphere of positive charge, and that there was a sphere of positive charge holding these electrons together. There had to be, because the electrons were all negative, and we haven't talked too much about it yet, but electrons repel each other. That was back from the chapter when we were talking about ions. Negatives repel, positives repel, but negatives and positives attract, and so The positives would need to be there to stabilize this model. Now, this was a nice hypothesis, right? But you got to prove it. So Rutherford, a different scientist, came around in 1909, and again, this J.J. Thomson stuff was around. Actually, I don't know when it was around. He was alive. He was probably alive. This was probably a concerted effort. Rutherford's working on the same sort of idea. He comes up with an experiment. It's called the Rutherford gold foil experiment. And in 1909, they shot tiny particles called alpha particles, and they directed them at a thin sheet of gold foil. Now, an alpha particle, since we're in chemistry, I can tell you what an alpha particle is. An alpha particle is essentially just a helium nucleus, okay, without any electrons on it. So it's just a helium missing its electrons. So that means it's got 2 protons, there's 2 neutrons. We can even kind of show it like this. We got our protons. And then our neutrons. And this thing carries a charge. Now, alpha particles are emitted as radioactive decay. When unstable elements decompose, they shoot out little, sometimes just energy, sometimes just electrons that we call beta particles, and sometimes they shoot out actual chunks of protons and mass. And that's what an alpha particle is, so it's fairly heavy. Now, the idea is that they're going to shoot these particles that are already themselves positively charged at this gold foil. And what they saw was that most of the particles actually passed right through the gold foil, but some got deflected. And some got deflected at really sharp angles, like back at the detector or off to the side. And the only thing that essentially could do that would be something else that's very, very positively charged. Now, the idea was that as these alpha particles went through the plum pudding model, that we shouldn't see that kind of thing because, if this is gold and it's positively charged, that positive charge is spread out over this entire atom and not concentrated enough to reflect an alpha particle that has a 2+ charge on it. But what we ended up seeing was that sometimes it did happen, it did get reflected. And so what that told scientists and what we believe today is that most of the atom is empty space, okay? And that all of the charge and all of the mass are actually located right in the center, in a small little bit inside the atom that we call the nucleus. Okay, so this is the summary. Sorry, this is the summary of what we've learned. Most of the atomic's mass and all of its charge are in the nucleus. Most of the volume of the atom is empty space. And the number of negatively charged electrons on the outside is actually equal to a number of positively charged particles on the inside called protons. Okay? And so in this image, this one here, in this image, the nucleus is greatly enlarged and the electrons are portrayed as particles. We don't really know if that's exactly true. Electrons are dispersed throughout the large volume. They weigh almost nothing. They're often described as wave functions. And if this was real and these protons were actually big enough to see just like this closest electron here would actually be like half a mile away, right? This distance, it would have to be half a mile away for this to be an accurately sized, scaled picture showing a nucleus that big. So very much enlarged graphic, but that's the case. Okay, so it looks like this is the chapter where we actually learn all about charge. So this will help us kind of remember positives and negatives attract, others same charges don't attract. Okay. Now, I don't want to say anything about that. We know the charge and the relative charge of the electrons and the protons. The protons and neutrons are very similar in mass, as you can see here. Electrons have almost a negligible mass compared to them. It's like 1/2000th of the mass. You can use this data table when you're solving your problems. This will make your homework a lot easier. The proton, we give a +1 charge, the electron a -1 charge. And the neutron, as its name suggests, is neutral. Now, we didn't go over the experiment where the neutron was discovered, but there were, in pure samples, when they started to separate them based on charge, they would sometimes find multiple signals within a certain element that led them to believe there was differences between the atoms, and there was mass differences. Some elements were heavier than others. I mean, some atoms of, let's say, copper are heavier than other elements, than other atoms of copper. And this has to do with isotopes. Now, and I think maybe we're going to talk about that in this chapter. Okay, and so again, charge equalization is something that nature wants to take care of. Atoms have the same number of electrons and protons because nature likes to be balanced. And the result of lightning in the air is that nature balancing. It happens too when you rub electrons off or onto yourself, when you cross the floor with your socks on, and then when you touch a doorknob, you're just balancing out. And sometimes that causes a release of some static buildup. Now, atoms and elements do differ from one another. Elements are defined by their number of protons. Sorry, how do elements differ from one another? The number of protons that they have determines what kind of element that you are. If you have a different number of protons, if you're an atom with a different number of protons than another atom, then you guys are different atoms. So helium nucleus, for example, has 2 protons in it, and an aluminum nucleus has 14 protons in it. And we often depict the atomic number, or we often represent it as the symbol Z. So Z here stands for the atomic number. It's also the number of protons. This is the periodic table of the elements, all the known elements and their atomic numbers. You can see the big number at the top. That's the atomic number. That's the number of protons. Now, the atomic mass, we haven't defined how that average, and that is an average. It's a weighted average. We haven't defined how we get that yet. But it is essentially the mass of the protons plus the neutrons. That essentially will give you the atomic mass. And then, of course, the number of electrons will equal the number of protons in a neutral atom. That means that there's also non-neutral atoms, and we'll have to talk about those. Just in case you were wondering, these 2 bars down here at the bottom, they fit into these little gaps right here. It would be a really big periodic table to have them sort of inserted there. Also, don't forget that 2 goes right into 3. They may seem like they are far apart, but they are right next to each other on this periodic table. The best way you could do a periodic table would be to wrap this around a cylinder so that the ends can touch up again, and that would be really cool. Okay, so let's talk about names real quick. So most chemicals are based on the English name of the element. Some are in Latin. The symbol for potassium is K, for example. That's Latin for kalium. The symbol for sodium, Na, it comes from the word natrium in Latin. Other elements are based on Greek or Latin. Lead is plumbum, mercury is hydrogarium, iron is ferrum, silver argentum, tin, stannum, copper, cuprum. This is why Cu is copper, cuprum. Let's see. Some come from early scientists that discovered these things, these elements. So polonium come from France. From Poland. They discovered it in Poland. Francium in France. Mercurium from Marie Curie. Let's see, who else? Argon actually was named from the word argos for inactive. Helium was named for Helios, the sun. It was discovered in the sun before it was discovered here on Earth. Okay. So that's where a lot of these names come from. Now, we get patterns, or we look for patterns in the periodic table, and the first guy who sort of did that was Dmitry Mendeleev. Now, he was a Russian chemist and professor. He proposed from observation that the elements are actually arranged in order of increasing relative mass, and that certain other properties kind of recur periodically. So what he did was he took the periodic table and he just laid it out from smallest element to biggest element, and then he sort of wrote down a bunch of stuff about each of those elements, and he saw that there was a repeating pattern. Lithium, sodium, potassium all behaved the same. They all formed the same. Oops. They all formed the same kind of compounds with oxygen. They all formed the same. Sorry, I completely messed up what I was trying to do here. I was trying to show you while I talked that lithium forms Li2O, that sodium forms Na2O, that potassium forms K2O. The same ratio of element to oxygen, 2 to 1, 2 to 1, 2 to 1. It's a repeating pattern. And so if we end up changing the periodic table's organization to stack those elements that are similar to each other, we get something that looks a lot like what we have today. Now, Mendeleev's periodic law was based on observation. Like all scientific laws, the periodic law summarized many observations, but it didn't give the underlying reason for that observation. Only theories will do that. So the patterns are law, but they don't explain anything. And for now, we'll just accept that. In Chapter 9, we'll come back and look at a powerful theory that actually explains that law and gives us those underlying reasons. Now, let's locate some families of some groups. So let's find the metals. Now, the metals are on this side of the periodic table. And let's talk a little bit about metals. Metals, they are good conductors of heat and electricity. They can be pounded into flat sheets. It's called malleability. They can be drawn into wires. That's their ductility. They're often shiny. We call that lustrous. They tend to lose electrons when they undergo chemical reactions. You should write that down. Lose electrons. And they're also, they lose electrons. And some good examples would be iron, magnesium, chromium, aluminum, sodium, gold, right? You like those. Okay, the next group is the nonmetals. The nonmetals are found here on the right-hand side of the periodic table. So metals on the left, nonmetals on the upper right. The dividing line between those is a diagonal zigzag line that runs from boron to astatine. The nonmetals have more varied properties. They are solids at room temperature, some are gases. As a whole, the nonmetals tend to be poor conductors of heat and electricity. They tend to gain electrons in chemical reactions. And oxygen, nitrogen, chlorine, iodine, those are some good examples of them. Now, we have the metalloids. Now, the metalloids are on that zigzag line. The metalloids are called semimetals sometimes. They display mixed properties. Sometimes they're called semiconductors because of their intermediate electrical conductivity. It can be changed, it can be controlled. This actually makes semiconductors really useful in electronic devices. They're central to computers, cell phones, modern gadgets. Silicon, arsenic, germanium. Those are good examples of the metalloids. Silicon actually shown here. So, metals, nonmetals, metalloids. Now we also have some other classifications. We have main group elements. Now these are the ones essentially that have tall columns. These are the main group elements. Their properties can generally be predicted based on their positions. Okay. Now, then there's the transition elements. Their properties are less predictable based on their position. So we separate them. And I'll give you an example. Main group elements, we tend to know their charges. We tend not to know these guys' charges because they can have what we call variable charges, and these other ones are invariable. Oxygen is always 2 minus. I wanted to write it like this. 2 minus. Always. Beryllium. Always 2 plus. But chromium might be 3 plus, might be 4 plus, might be 5 plus. And it's not that I don't know, it's that it depends. So we separate these guys. Let's talk about families. We have some families that get names, some that don't. We have the group 1 metals. We call these the alkali metals. So family name, alkali. Group 1 is just what it's called. Group 2, the alkali earth metals. We've got group 7, the halogens. We usually have Roman numerals also showing these. And then group 8, the noble gases. So you can see here there's also transition metals, get a family name. We've got lanthanides and actinides as well. We're not going to deal too much in the lanthanides and actinides. Now, why do we group them as families? Well, because remember when we stack them, their properties tend to repeat. And so we like to be able to classify the kind of activity we're going to get from certain families. For example, the alkali metals. Included in this picture here, you see lithium and then sodium down here in the second picture. Both of these, sodium here is reacting with water. Potassium, rubidium, cesium. These guys are very reactive with water, in fact, explosive in water. Alkali earth metals, not so reactive in water, still reactive. The second one here is calcium reacting with water. This first one here is magnesium giving off a lot of really bright light and heat. Magnesium was used in old flash bulbs in the old days for their bright light. But they all have similar reactivities, similar patterns. Now, of course, as you go down a column, elements become more metal-like. So which means there is variability within columns in terms of how much activity we see. Now on the other side, we've got the halogens. These are usually gases, with the exceptions of bromine's usually a liquid. Chlorine's shown first, poisonous gas. Bromine and iodine. Iodine's shown here second. These are iodine crystals. And then we've got, of course, if you dissolve iodine in solution, it turns yellow. So if you're familiar with a yellow iodine solution, that's in water. This is iodine crystals, they're purple. And then astatine. These guys are poisonous usually. That's why we use them for sterilizers and for antiseptics. And then the noble gases. We call these the noble gases, of course, named after inactive, argon inactive, because they don't interact with the other elements. These were the last to actually be found in the periodic table, right? We've got this periodic table. The noble gases are actually here, and they were not on Mendeleev's periodic table. He was missing them all together because he couldn't find them. They didn't react with anything. So, and this includes neon, helium, argon, krypton, xenon. Okay, so in chemical reactions, atoms will lose or gain electrons and form particles called ions. Now, positive ions are called cations. Negative ions are called anions. I always remembered this because positive looks like a little T, and cation has a T in it, and that's how I remembered it, but you can figure it out. The charge of the ion is always shown in the upper right-hand corner of the symbol, and they're usually written with the magnitude of the charge shown first, like 2 or 3. And so some examples would be like Mg2+, or you can actually see them over here, Mg2+ and O2- as ions. Now, metals, remember everything on the left-hand side, you'll see form cations because they tend to lose electrons. So what does that mean? That means the lithium atom has now become a lithium atom that doesn't have an electron, and so we show that electron as being gone, and that minus that it's carried away with it reveals that there's a positive, a proton essentially, that's unbalanced, right? Nature wanted to balance, and now it's unbalanced. On the other hand side, other side, we've got nonmetals. Nonmetals tend to gain electrons. And so we've got an atom here that now has an extra electron. We've added them together, and that conveys this negative charge now. It's got an extra charge. The more electrons you have, the more charge you have. Let's get this straight right off the bat. You can't lose protons, okay? You can gain or lose electrons, but you cannot lose or gain protons. So that should have some implications on how the charge is able to change, right? If you could add protons, you'd be adding pluses. If you could remove protons, you'd be minusing pluses. But we can't. We can only do electrons, and electrons are minus, and we can add them or we can subtract them, but that's it. Okay, if you need a formula, the ion charge, sorry, easily frustrated. The ion charge is going to be equal to the number of protons minus the number of electrons. So if you are given those numbers, for example, if I say you've got an atom that has 13 protons and it has 12 electrons, what's the charge? It's going to be +1. If I say you have 18 protons and you have 20 electrons, what's the charge? -2. So that's how you would use this equation. Okay. So again, protons minus electrons, and you'll be able to figure out how many they have. Now, if you were given a problem like this, if they said, go all the way back to this, sorry, to this periodic table. If I said you have 27 electrons in your copper atom, what's the charge? And that's all I told you? I expect that you're going to be able to look up copper, find its number, and say, oh, that's the number of protons. 29 minus 27, 2 plus, right? Does it make sense that copper would be positively charged? Yes, because copper is a metal, and metals become positively charged. Metals don't usually become negatively charged. Metals are good at conducting electricity, losing their electrons. Not the other way around. Okay, so that's how we would basically go ahead and form an ion. Now, before we move on to isotopes, let's hang out on this slide one more minute so I can show you what I mean by set charges, or main group elements and their invariable charges. So you can go ahead and memorize these, or you can refer to these tables often, but notice that the group 1 ions are all +1 ions, and that the group 2 ions are all +2 ions, and that group 3 in our main group, right, main group, because this was a transition, are all 3 plus. Now, we don't see a lot of ions from this row, but they are 4 plus and they are 4 minus, because they're right in the middle. And we haven't gone over the reason why these charges are the way they are yet. Right now, let's just memorize that. Later, we'll understand it a lot better. If we start to work backwards from the noble gases, these guys are -1, these guys are -2, and these guys are -3. So you can see a little bit of a pattern there, right? A little bit of an overlap there on column 4. But I would memorize these. These are going to help you when you're writing formulas, when we're trying to figure out the charges on certain atoms. This is going to be able to give you an idea of at least these atoms and their charges. Now we'll have to come back and talk about all these guys down here. All right, now in addition to ions, we have isotopes. Now, when the number of neutrons varies, we get heavier and lighter versions of an atom. So this is one of those exceptions to the rule that says all of the atoms are the same kind. Now, they don't have the same number of neutrons. We call those isotopes. Isotopes, like the baseball team on The Simpsons, if you watch The Simpsons. All elements have their own unique percent natural abundance of isotopes. So as an example, I'm showing you neon. And so neon here has 3 naturally occurring isotopes. Neon 20, and I'm showing it to you the way it's written, 2 different ways. So neon 20, neon 20. I'll just show you all these and then we'll go and explain. Actually, we'll explain it now. So what we're seeing here with neon 20 is that we've got the symbol shown in Ne, right? We've got the mass number on top. So this is the total of the protons plus the neutrons. And then the atomic number shown on bottom down here. So that's the number of protons. And so what we get by looking at this is some simple math, right? 10 over, or 10 from 20 is just 10. So that tells us that the number of neutrons in Ne20 is 10. Now, there's another version of showing that same information, and that's just writing it as Ne20 like that. Now, the difference is Ne, they don't take an extra step to write a 10 somewhere so that you know neon is number 10. It's assumed you can look up neon on the periodic table and find out it's number 10. Now, getting back to this, now neon 20, I don't think we have, neon 20 actually makes up the majority of the isotopes of neon. 90.48% of all neon atoms are neon 20. Then we have neon 21. This is a heavier neon because we can see here the mass has gone up. It's 21 now. That doesn't change the number of protons, so the number of neutrons has gone up to 11. Neon 21 actually makes up the smallest percentage of the isotopes of neon, only 0.27%. And then neon 22 is roughly 10%, 9.25% for neon 22. And this one would have 12 neutrons. Okay, so the mass number in A, the Z is the proton number. A few different ways of showing it. Now, we figure out that isotopes have that exist because, again, I was telling you we separate atoms based on their charges. What I mean is we pass them down a long corridor, but we send them through a magnet. So this is the magnet right here, and we've got this beam of particles we're shooting this way. Now, all of the neons would have the same charge, assuming that we could knock an electron off of these. And so they would all be carrying a positive charge. And so they would all get deflected from the positive pole and attracted to the negative pole. So they would all have a path like this. And they'd hit the detector somewhere. But neon 21 would be harder to move off of its path than neon 22. Have you ever tried to push someone while they're running, or a big person while they're running? They're harder. It's more energy to move them. And so we end up with slightly different paths, each path corresponding to one of the different isotopes, and the thickness of the spot corresponding to the percentages. So that's how we find out that these isotopes exist. Now, we care about isotopes because we need to know how much of each there are so that we can get an average mass to put on the periodic table. The periodic table's atomic mass is actually an average of all the different isotopes. We can look at these right here and see that neon 20 is the majority of the weight. What I mean is the major percentage of neon weighs neon 20. So if we were just to take an average of 20, 21, and 22, of those three numbers, the average would be 21. But if you go and look at the periodic table, the average mass, or the mass of neon, is actually much closer to neon 20, or to 20 than to 21. And that makes sense because there's a lot more of those atoms that are near the weight 20 than there are near the weight 21, or 22 for that matter. So how do we calculate that? Let's do a problem. So here I have a problem for us. So we've got naturally occurring chlorine. Chlorine has two isotopes, chlorine 35, chlorine 37, and the exact masses are included. So 34.97 atomic mass units for chlorine 35 and 36.97 for chlorine 37. The percentages are also given. Notice that they add up to 100. That's what percent means, per 100. So if 75 is one of the percentages, even if I don't tell you what the other one is, you should be able to figure it out because they add up to 100 always. To figure out the atomic mass, the one that we see on the periodic table for chlorine, we need to follow this formula. And this formula basically goes like this. The fraction of the isotope Let me write it this way. I'm going to say the decimal percent. Hope you guys know what decimal percents are. Decimal percent. So if 75.77 is the percent, the decimal percent is when you take that and divide it by 100. So 0.7577. So you take the decimal percent of one of the isotopes and you multiply that by the mass of that isotope. And then you keep that number. And then you add that to the next round of isotopes. The decimal percent times the mass. And so it's important here that you pair up the correct masses with the correct percentages. If there's 3 isotopes, like there was in neon, then you add a third round of decimal percent times the mass. This is actually how your grade is calculated. We have 6 rounds. We have exam, and then lecture quiz, and then lab, exam, and then homework, and then lab assignment, or whatever, right? But each one of those has their own percentages, and then you'll have your own average score. And if you want to calculate your grade, or at least confirm that Canvas does a good job of calculating it for you, you can do that. Okay. So that was a problem that we kind of worked out together, or you could see the answer to. Why don't you try this one? Or we'll work this one out together too. So first, gallium has 2 naturally occurring isotopes, gallium-69 and gallium-71. Now the percentages are given. We need to calculate the atomic mass of gallium. Now this is too easy to give you on an exam because the atomic mass of gallium is what's on the periodic table, and you could go find that out. But what is something I could give you is I could actually ask you for the mass of, let's say, gallium-71. And you would have to work backwards. You would have the atomic mass already. Check. You would have the percentages already, 0.3989 and 0.6011, and let's see, for 0.6011 the mass was 689256 AMUs, and then you just wouldn't know what this one was, and you'd have to do some algebra and you could figure it out. But that's not what this problem right here exactly is, and so let's just do this problem the way it's kind of presented. Here we are finding out what the mass is, and so we just need to fill in the numbers that go here. 70.9247 AMU. So if you do these, I think I have it kind of already here for us. If we divide by 100, we get the decimal percents. If we plug in those decimal percents and their masses into the equation, we get 41.4 for the first number, 28.29 for the second number. We add those together. Now, going back to the number of sig figs, you can see number of sig figs here would be 4 for our limiting number. But then it becomes a decimal point problem for the second step. Here you see it's 4 places past the decimal. 4 places past the decimal. So then we'd do that. Now, at the end, we have to, we would have, in this first step, we would have used 4 places past the decimal, or 4 sig figs times 6 sig figs. So we would have only been able to keep 4 sig figs. So we would have had to cut our answer, or pretend like our answer only had 2 places past the decimal. That's why we're limiting it there. But that's how you would do this type of problem. Now, I do encourage you guys to try these on your own. There will be one of these on the quiz. And like I said, as a challenge, I'll either make up an element for the exam so that you don't have a periodic table to just get the atomic mass from, or I will give you the atomic mass and ask you to get one of these masses instead. And again, that's just a little bit of algebra. Either way, you're going to need to practice these. So give it a shot. All right, so in this chapter we talked about the atomic theory. We looked at the nucleus and the atom, the nuclear model. We talked about charge, protons and electrons having their charge. We looked at the periodic table, talked about the columns, the elements, the families, where to find metals and nonmetals, what the atomic number is and how to find it. We looked at ions, we looked at isotopes, and as far as learning objectives go, I've listed them for you here. So, yeah. Hopefully this is helpful, guys. Good luck, and I'll see you guys next time.